Okay, so in chapter 8, we're going to be looking at carbohydrates. And carbohydrates are made of carbon, hydrogen, and oxygen. They are a large class of naturally occurring polyhydroxyaldehydes and polyhydroxyketones. Monosaccharides are the simplest of carbohydrates, and they're referred to as simple sugars. And they have 3 to 7 carbon atoms and 1 aldehyde or a ketone. So if it has an aldehyde group, then it is classified as an aldose. But if it has a ketone group, then it is classified, or the sugar is classified as a ketose. So the aldehyde group or the ketone, the aldehyde group in the carbohydrate is always located at the very top, or carbon number 1. Okay, and then the ketone in the monosaccharide is always located on the second carbon. So we know ketones can't be located on the first carbon, so it has to be located on the second one. And then at the end of the carbohydrates, there's always a ch8 group at the very bottom. So we're going to talk about the green part, what's there, in the next slide. Okay, carbohydrates have names ending in OSE. So for example, we have glucose or fructose, or ribose. So all of those that are listed there with the structures. So a monosaccharide with 3 carbon atoms is referred to as a triose. And then 4 carbons is a tetrose, 5 carbons is a pentose, and 6 carbon hexose, and 7 heptose. And then in between the aldehyde and the ch2OH. So here we have the aldehyde and ch2OH. We have hydrogen and a hydroxyl group on each of these carbons. Okay. So same thing over here. So that's glucose and it's a hexose. We have an aldehyde group, a ch2OH, and then we have hydrogen and hydroxyl groups attached to these carbons here in the middle. Okay, the last one, fructose, is a ketose, and it's a hexose. So there's our ketone, and at the bottom our ch2OH, and then we have the hydroxide and hydroxyl and the hydrogen attached to the carbons here in the middle. Monosaccharides are referred to as the simple sugars, like we stated on the first slide, and they can undergo a variety of structural changes and reactions, and we'll look more into those a little bit later in the chapter. But monosaccharides can react with each other and form disaccharides or polysaccharides. And their functional groups are able to react with alcohols, lipids, and proteins to form biomolecules. So again, we'll look more into that later in the chapter. So chiral compounds exist as a pair of enantiomers. So basically that just means that they're mirror images of each other. And it can have either a D form or an L form. So we've talked about carbons in the past, and we said as long as there's 4 different groups attached to the carbon, then it's considered a chiral carbon. So this one, would not be considered chiral, neither would this one be, but this carbon right here is. Okay, this carbon has the OH, the hydrogen, and then the COH, and this one CH2OH attached to it. So 4 different groups are attached to that middle carbon. So that one would be chiral. Okay, but the last one, let me see if I can go back here. Okay, this last one right here has carbon, 2 hydrogen, hydroxide, and then this whole thing attached. So all of this attached to this carbon. So this carbon wouldn't be considered chiral because it has these 2 hydrogens. Okay, so if it doesn't have 4 different groups attached to the carbon, then it's not considered chiral. Okay, so again, these are just enantiomers, and they are mirror images of each other. So they're either going to be a D form or an L form when we're talking about the carbohydrates. So this one right here is the D form, over here L form, and you can see the only thing that's changing is the placement of the hydrogen and the hydroxide. So on this one, the hydroxide is on the right side. On this one, the hydroxide is on the left side. So again, enantiomers are just stereoisomers that are mirror images, but they're not superimposable. So they have the exact opposite configuration at every chiral carbon. And then diastereomers are stereoisomers that are not mirror images of each other. So they're going to have the same formula, but they're not going to have the same arrangement. So here's an example. So compound 1 and 2 are, let me write this down before I say it, erythros. 3 and 4 are threose. Okay. So 1 and 2 would be considered enantiomers because they are mirror images. So again, we have, the aldehyde up here, the CH2OH groups on the bottom, and the only thing that's different are these OH groups. So on compound 1, they're on the right side. Compound 2, they're on the left side. So it's an exact mirror image. Okay, same thing over here. We have the aldehydes up here, CH2OH groups down here. But the OH on this one is on the left side. The OH over here is on the right side. And then they're the exact opposite for compound number 4. So those are 3 and 4 are mirror images of each other. So 1 and 2 are enantiomers, 3 and 4 are enantiomers. But if we were to compare compound 1 and 3, okay, those would not be mirror images, right? So we would call those a diastereomer. And then compound 2 and 4, same thing. It's not a mirror image, but it does have the same formula, just a different arrangement. Well, not even different arrangement, but they're not superimposable. They're not mirror images. So there would be a diastereomer. Okay, a Fisher projection is drawn with vertical and horizontal lines, and they represent the carbon chain. So the Fisher projection here is right here. Okay, and so again, the aldehyde is always at the top, and the CH2OH is always at the bottom. And so anytime you have anytime you have the elements or the groups projecting above the page, those are going to be on the left and the right of the chiral carbon. So chiral carbon is right here in the middle. So to the left and to the right, they're going to be projected above the page. So these two are coming up above the page. Okay, and then those that are projecting behind the page are above and below the chiral carbon. So that's going to be the aldehyde and the CH2OH group. So that's going to be behind the page. So, we draw them in this Fisher projection, but that's not actually what the geometry looks like. So we can see a better idea of what the geometry looks like with this ball and stick model. But normally the carbohydrates, when we draw them 2D, are drawn in the Fisher projection. Okay, monosaccharides are divided into L and D sugars, so based on their structural relationship to glyceraldehyde. So in the D form, the OH points to the right. So if you have a D sugar, the OH is going to be on the right side. On the L sugars, the OH is going to be on the left side in the Fisher projection. Okay, now if you have more than one chiral carbon, because again, this is our chiral carbon right here. If we have more than one of those, then we always look at the chiral carbon that's furthest from the carbonyl group. So the ones that are highlighted here, those are the ones that are furthest from the carbonyl group. So those are the ones that are going to determine if we have a D sugar or an L sugar. So because OH is on the right side, it's going to be D. And over here, OH is on the left side, so it's going to be L. And then same thing over here, OH is on the right side, so it's going to be D. OH is on the left side, so it's going to be L. So you can see, they're mirror images of each other. So all the OHs are on the right side here. So in the L form, they're all on the left side here. Okay? But for glucose, we only have, we have one that's not on the right side. All the others are on the right side. But when we look at the mirror image, now we have these OHs on the left side and just one on the right side. So we can use that last chiral carbon to figure out whether we have the L or the D sugar. So the only thing that's different for these enantiomers is the way they affect polarized light. So we're not going to get into that too much, but polarized light passes separately through a pair of enantiomers. And basically what happens is they just rotate the light in the opposite direction. Okay, so that's about all we're going to cover with that. So that's what makes it different. Okay, D-glucose is one of the most abundant of all monosaccharides, and it can exist as an open chain hydroxyaldehyde or as a cyclic hemiacetal. And the most stable form for a pentose and a hexose is a cyclic hemiacetal. So we kind of looked at this when we were talking about aldehydes and ketones, that they are able to form these cyclic structures. But just to show you here, okay, so we have the aldehyde here, and then we have the OH. Because remember, let me go to this one. Aldehyde plus an alcohol gives us a hemiacetal. So the hemiacetal has the OH group and the OR group. So we're going to form that with the monosaccharide. So what happens is we can turn the Fisher projection 90 degrees and then fold this 6 carbon, we kind of bring it around to come over here and make a hexagon because we have 6 carbons, okay? And now the aldehyde is able to react with an alcohol or an OH group, but it's actually not going to be this one here, okay? So it looks like it would be, but it's not. It's going to be this aldehyde and this alcohol that are going to form the hemiacetal. So I'm just going to draw that for you. Okay, so we get, we've redraw this here. Okay. Okay, so we've curved it around, but what we're going to do is we're going to basically switch spots with these two, okay? So if I redraw this, because they're both attached to carbon 5 here, right? Oh, there we go. This is carbon 5. So this one's 1, 2, 3, 4, 5. So instead of showing carbon 6 over where I had it, I can put it up here. Okay, and now my OH group is here. So I didn't do anything crazy. I just switched the way the OH was shown and the CH2OH is shown. They're still attached to that carbon 5. Okay, so now the reaction is going to take place right here between the aldehyde and the OH group. So we're going to get the hemiacetal that forms. Oops, I didn't mean to erase that whole thing. Okay, so we have the oxygen, and then it's attached to the carbon. Okay, I'm drawing all their hydroxide groups here. Oops, not sure what I'm doing. There we go. Okay, so now we form the cyclic hemiacetal by combining the aldehyde and the OH group. So the OH groups, let me go back here. So the OH groups that were on the right are going to point down. So when we draw the cyclic structure, it's called a Hawthorne structure. So anytime we draw the Hawthorne structures, the OH groups that were on the right, which, are going to be these right here. Those are the ones that are on the right. This one was on the left. So if they're on the right, we're going to point them down. Okay, so you can see these are the 3 that were on the right. Okay, and then if they're on the left, they're going to point up. Okay, so that's how you would draw the Hawthorne structure. Okay. So the cyclic monosaccharides that differ only in the OH position on carbon 1 are called anomers. Anomers. So when we wrap it around, then the hydroxyl group right here on carbon 1 is what we're looking at. So it can either be going down or it can be going up. Okay, so that's what we're talking about there. So it's a very small change. So this obviously is still D-glucose, but we went from alpha D-glucose to beta D-glucose. So that small little change can account for a lot of differences when it comes to digestibility of starch and cellulose. So we're able to digest starch but not cellulose. And again, that's just that one little change, whether in the position of the hydroxyl group. So in an aqueous solution, the alpha D-glucose opens to give the open chain. Okay, so here, if we put alpha D-glucose into water, it opens up to give the open chain D-glucose. And then we have our aldehyde again, right? So over here, it's a hemiacetal, and over here, we've got our aldehyde again. So the open chain can close because the carbonyl group reacts quickly to form the hemiacetal again. And so as the ring opens and closes, the OH group on carbon 1, so the one we were just talking about, this guy right here, can form either the alpha or the beta anomer. And so it can do both. It can form the alpha and the beta as well. So when this happens, it's referred to as mutarotation. Can't say that. Okay, so again, when we put it in water, the chain will open and close and form the alpha and the beta D-glucose.